A very good morning. And it's my pleasure and privilege to be a part of this co-located event at KubeCon. My name is Janakiram. I currently run an independent consulting business from Hyderabad, India. I'm a certified Kubernetes administrator, app developer, and closely tracking this space for a few years. So I'm going to walk you through the current state of this state when it comes to cloud native storage. So essentially, I have three parts. The first one is the evolution of stateful workloads when it comes to cloud native and container native. Second thing, I want to touch upon how CSI has changed the game and how it has become the critical milestone in this journey. The third thing that I want to talk to you about is what is the current lay of the land, what is the current landscape, how things are looking, and what is the road ahead. So those are the three essential sections of my presentation today. So let me start off with the very first thing, the evolution of stateful workloads. So before I go any further, I want to set up some nomenclature and terminology. It's not that you're not aware of that or anything, but just make sure that we are on the same page. So I call this as cloud ready. So cloud ready is essentially what we have been seeing for the last decade, which is completely virtualization, hypervisor-based virtualization, where we have the three components, three building blocks, compute, storage, and network that are available as virtualized. Security and management happens to be the layer on top of that, and we run many cloud-ready applications. So cloud-ready applications, according to me, is a kind of a category of applications that are not designed for cloud, but they are capable of running in the cloud. So think of the legacy Oracle database or an SAP instance or a legacy line of business application that is supposed to be running on a bare metal x86 machine, but that can be quickly packaged and deployed on a VM is a cloud-ready application. And then, of course, we have the cloud native, where we have a level above the cloud ready, and we have container native storage, container native compute in a lot of ways, and container native networking. And then to manage this, we have an orchestration layer. Security and management happens to be the consistent layer on top of that. And we have the modern, contemporary microservices as the cloud native applications. So cloud ready is anything that ran on top of VMs directly, typically either in a private cloud in a data center or even in the hyperscale in the public cloud. And cloud native is basically start with hyperscale and bring it down to the data center. So that is just setting up the stage and making sure that you follow the convention that I'm following, which is cloud ready versus cloud native. Now, one of the startling fact that I have seen in the last decade or so is the state always being afterthought. What is very interesting and very startling is the fact that state comes in much later than the compute. So if we actually go back and look at some of the cloud-ready evolutions, Amazon EC2, the beta 2 was launched in 2006, and EBS was launched only in 2008. It took a good 2.5 years for Amazon to basically stabilize block storage and launch it as the attached storage for EC2. Same thing is the case with App Engine. So App Engine was one of the very first platform as a service offerings in the market, which actually went live in beta sometime in 2008. It was a highly opinionated PaaS, no file system, no block storage, no persistence baked into it. Google gave Cloud Store and a couple of other choices, but it was very, very restrictive in terms of managing state. And same is the case with one of the early implementations of Azure, which was back then called as Windows Azure. And Microsoft, again, didn't really bring persistence on day one. It was web role and worker role, if you remember, and that really didn't have any storage. It was all ephemeral, it was all stateless, and the object storage was the only mechanism to basically persist state. So this has been a trend, and what is very concerning is, why do platform architects bring state later than compute? And if you are wondering what's with cloud native, well, even with cloud native, it's not very different. When Docker came out, it was all about the union file system and containers being ephemeral, containers being stateless. And it took a while for the Docker ecosystem to catch up with the volumes and basically bringing in state and persistence. Same thing with Mesos. Persistent disks came in much later. And even with Kubernetes, the very first version that Google went live as a managed service, and even the upstream Kubernetes, had very primitive support for state. So historically, traditionally, state is always an afterthought, whether it is cloud ready or cloud native. And this is actually hurting a lot of end users and enterprises who are trying to adopt emerging technologies. But if you actually look at the 4 critical attributes of production systems, right? By no means this is the most comprehensive list, but these are the basic checkboxes that most of the companies, most of the organizations click before they go live. Scalability is very critical. An application has to expand and shrink based on the demand. And then we have security, a no compromise capability of production applications. Then reliability, your application should be really available and it should be reliable. And finally, availability. And reliability and availability are mutually exclusive and independent. But these are the critical capabilities of any production system. Now, if we look at the current state of production systems, particularly on cloud native and cloud ready, we have been focused more on scalability for stateless and reliability for stateful. So again, bringing in the analogy of cloud ready versus cloud native, in cloud ready world, the reliability is delivered by a variety of stateful systems. For example, object storage, managed databases, a distributed shared file system, block storage will ensure your applications are durable and reliable. And in terms of the scalability, most of the hyperscale providers give us autoscale. And autoscale covers a lot of capabilities when it comes to the availability and the scalability of applications. For example, if you take Amazon EC2's autoscale, just before you enable autoscale, you got to make sure you have a health check. You need to make sure that you have a load balancer configured. So a lot of checkboxes get clicked even before we enable autoscale. So that takes care of a lot of capabilities in terms of availability of the system and scalability of the system. And in terms of durability and reliability, it's all delegated to the underlying managed services like block storage as a service, managed databases as a service. So today, if a customer is going live on a hyperscale infrastructure platform, reliability is delivered by managed services, and scalability is delivered by autoscale that is available through some configurable options. And it doesn't matter whether we are talking about the managed instance groups and autoscaler on GCE, or it is virtual machine scale set on Azure, or the launch config and autoscale group in EC2. Essentially, we have exactly similar capabilities in each of the hyperscale environments. Now, when it comes to cloud native, we have a slightly more granular and more broader choices. Currently, when we look at Kubernetes, the durability and reliability is confined to persistent volumes and persistent volume claims. This is where traditional storage admins will step in, and they'll actually create persistent volumes out of their existing environments. And they become claims before they can get consumed by developers and DevOps who are actually scheduling pods on Kubernetes. So currently, a lot of durability and reliability is dependent on the way persistent volumes and claims are being managed. This is comparable at a high level, not exactly apples to apples, but at a high level, this is compared to the block storage of cloud-ready providers, cloud-ready systems. And when it comes to ensuring scalability and availability, we have a much better approach here. Now, thanks to the design of a controller architecture in Kubernetes, you can design a stateful set which will bring in a stateful cluster into the realm of Kubernetes. We have deployments which will enable the desired state of configuration, roll back, roll forward, and doing PaaS-like deployments on Kubernetes. And then we have the autoscale through HPA, the horizontal pod autoscale. So those capabilities are actually ensuring the scalability of applications, but durability and reliability is still pretty much confined to the persistent volumes and claims offered by Kubernetes or the managed environment that is giving us the cloud native environment. So when we look at the challenges in dealing with these environments, particularly in the cloud native world, customers went through a journey. I have been working with many SaaS providers in India, helping them get on board with Kubernetes. And I've been working in this space for the last 4 years. So initially, Kubernetes gave us very primitive mechanisms to bring in state. It all started with empty dir, which will vanish the moment the pod gets terminated. Then we have slightly more long-term capability through host dir, host path. But again, that is an anti-pattern if you're actually doing real scale-based. Excuse me. So host path is basically pinning your pod to one of the nodes. Not a great idea, but that was the only option available. And then even config map and secrets made use of the basic storage primitives. The next iteration of using state in Kubernetes was relying on a distributed file system. So NFS using Ceph, GlusterFS, iSCSI, that brought us closer to actually doing more distributed, more scalable, stateful deployments. But the biggest setback with this approach is you need to SSH into every node, and you need to basically do a lot of plumbing and ensure that the node is ready even before you deploy your stateful pod. That means it takes away the cloud native operations where everything is controlled and monitored from kubectl. But here you need to make sure that your node is participating in a distributed file system, and then you go ahead and deploy your pods. But that was the only option available in the second iteration of managing state in Kubernetes. Then thankfully, we had hyperscale providers started to offer managed Kubernetes. So we had GKE, AKS, EKS, IBM Kubernetes service, and many more. So the block storage that hyperscale providers traditionally exposed now started to show up as a storage class within Kubernetes. And this was the third iteration, and it actually coincides with the maturity of hosted Kubernetes services. And today, most of the deployments that are going live on cloud are taking advantage of these primitives offered by cloud providers that are hand in glove with the underlying block storage. So if you're familiar with EBS, you can pretty much use the storage class and the volumes provided by EBS in your container and cloud native environments. And more recently, we are seeing this phenomenon of true born in the cloud, cloud native storage offerings. This is a level of an abstraction on top of block storage. So the biggest advantage of using cloud native storage when compared to the previous iteration of provider-specific, hosted-specific storage class is the ability of using the same set of tools that you typically use to manage Kubernetes and the workloads that are running on Kubernetes. Most of the container native storage offerings that you see bring in a level of abstraction. For example, if you take Portworx running in ECS or EKS, you have a set of nodes, and every node has a 50 GB of EBS volume attached to it. Some of them are SSD, some of them are just general purpose disks. And then you create a Portworx storage volume that basically pulls the storage from all these block devices and gives you a unified view of the storage. So you don't really need to deal with one EBS attached to one node, but instead you gain a kind of a view, a high-level view of a storage pool that is aggregated from multiple disks that are attached to your entire cluster. And this is the most recent iteration, and this is becoming the de facto for going live with Kubernetes. And this is becoming the most essential prerequisite for running stateful production workloads either in cloud or on premises. So this has been the journey that I have seen on how customers started to use state. But there are quite a few challenges with this. The first one is storage is still a silo. Now, Kubernetes ecosystem has evolved pretty rapidly in the last two and a half years. And today, kubectl is becoming a very powerful weapon It is the only tool that is used by a lot of admins to deal with the entire cluster, and even provisioning a new cluster thanks to Cluster API and some of the innovations that are happening in that space. But unfortunately, when it comes to storage, the ecosystem has to deal with two different silos. One, the traditional way of provisioning storage volumes and exposing them to the Kubernetes world, and then taking over with persistent volumes, claims, storage classes, and so on. Now, unfortunately, this is not integrated with some of the evolving tools and workflows. For example, we are now taking advantage of CI/CD by using canary releases, blue-green deployments, and a whole lot of agile techniques. But unfortunately, storage is not catching up with the evolution of the application deployment and application workflow. It is still a separate train that is dealt by a different set of professionals that may or may not understand how cloud native functions. And it is definitely not aligned with scale-out architecture. Now, one of the biggest advantages of customers using Kubernetes or cloud native is the ability to scale out. But because of the friction that exists between stateless and stateful, there is a wide gap between the way you treat stateless workloads and the way you treat stateful workloads. The gap is shrinking, but it is still a very significant, a wide gap that exists between the way you manage stateless versus stateful. And finally, this is not specific to storage, but I think the entire Kubernetes community and ecosystem suffers from this. We don't have the context of an application. Everything that is deployed in Kubernetes is a collection of pods, collection of secrets, config maps, services, persistent volume claims, and Kubernetes per se doesn't have the view or a context, or there is no boundary where you can say, this is my application and this is how I treat my application. The moment an application gets deployed in Kubernetes, it is spaghetti set of resources and objects. And that's the reason why there is a new way of looking at bringing in application awareness and application context. Some of the upcoming projects, like what Alibaba and Microsoft are doing with the object application model, which is called OAM, the open application model, and what Google is trying to do with Knative serving, Knative eventing, and what OpenShift is attempting, which has been bringing application context for a long time. So those are actually helping the application developers treat Kubernetes deployments as a logical unit of application. But it is much more challenging when it comes to stateful workloads. Unfortunately, these stateful operations don't operate under the context of application. You cannot really say, take a backup of all the PVCs that belong to my application. Now, the problem is Kubernetes doesn't understand application. So how do you take a backup of all PVCs that belong to an application? So that is one of the biggest challenges, where the PVCs, which are an inherent component of Kubernetes, don't operate in the context of an application. So now that is actually what I spoke about, is the end user or the enterprise challenges. Now, when it comes to vendors and the community, the list of volume plugins grows significantly in the last couple of years. Earlier, when Kubernetes was in 1.1 or even versions before that, it had a handful of plugins, which was easy to deal with. But over a period of time, the in-tree plugins started bloating the core Kubernetes distribution, and today there are over 24 such in-tree plugins that are directly interfering with the ability to ship the upstream Kubernetes faster. And the problem with this approach is the plugins that are actually very important for you to provision the persistent volumes, they force you to rebuild the entire Kubernetes distribution and deploy it for even a minor change. So it is more like an in-proc integration that forces you to go back and forth every time you modify a plugin configuration. Now, flex volumes was one of the answers to this problem, where you could separate out the actual plugins, but flex volumes are too fragile. So it is basically a binary that will take a set of parameters and can automatically provision storage outside of the context of Kubernetes. It was a stopgap solution. It was more like a Band-Aid that got applied to the problem of bloated Kubernetes distribution because of in-tree plugins, but that really didn't solve the problem. And again, storage operations are tightly coupled with the container orchestration engine. So everything that you do, for example, bringing in a new provider or managing the volume plugins, everything is so tightly coupled with container orchestration that you have to either wait for the next iteration or next release of Kubernetes, or you have to take the chance of rebuilding Kubernetes and deploying all by yourself. So these were the challenges faced by the ecosystem, and particularly vendors who started to contribute to Kubernetes distribution. Now, the biggest milestone came in the form of the CSI interface, which is basically the container storage interface, which is almost like a JDBC, pardon me for calling this, but for me it's a lot like JDBC, and more on that a little later. But it basically brought in a kind of a decoupling between Kubernetes universe and the storage universe. And now they can actually plug and play and interoperate without ever touching the source code or waiting for the next iteration to come in. So it is basically a standardization of how orchestrators interacted with storage. Now we call it orchestrators because this is not specific to Kubernetes. CSI can work with plain vanilla Docker, it can work with Mesos, it can work with Nomad, it can work with any other orchestration engine. It is not specific to Kubernetes. And there is a very clean separation between control plane and data plane. And this will open up a lot of opportunities for storage vendors to innovate and bring in additional capabilities without ever fiddling with the core distribution or the binary. And it promotes storage interoperability. This is one of the biggest challenges for end users. So switching from one storage provider to another has been pretty challenging, pretty complex, but thanks to CSI, which is decoupling the storage implementation from container orchestration, you can seamlessly switch between one implementation and the other. So I borrowed this diagram from one of the GCP blogs, and that's the reason why I call CSI as the JDBC. So JDBC or ODBC basically created an intermediary layer, and developer need not worry about the primitives of talking to Oracle or MS Access or SQL Server or DB2. And it gave a set of well-defined interfaces that any database vendor could implement, and the application will simply call the API to talk to a specific database. And that was ODBC or JDBC 2 decades ago. CSI attempts to bring something very similar. It basically brings in 3 sidecars as containers that sit in the cluster, and every time your application wants to leverage storage, it will basically go through a chain which will figure out what are the available features or capabilities of a specific storage vendor implementation. And based on that, it will call node-specific operations. Node-specific operations are like provisioning a new EBS volume, attaching it to the node, making sure that it shows up as /dev/SDF, and then container-level operations, which will eventually mount the EBS volume or the equivalent and showing that up in the actual pod. So all of these operations are completely decoupled and implemented as a separate interface. Some of those drivers and components run as daemon sets in Kubernetes. Some of them are running as sidecars. But the beauty is it's very easy for you to bring in a new storage implementation, register that with your environment, and start using it without ever touching your core cluster. So CSI, in a lot of ways, is a true game changer. And today, if you look at where we are in the journey, a lot of in-tree volume plugins are now gradually shifting to becoming CSI compliant. A lot of cloud providers are offering CSI compliant drivers for Kubernetes, either in beta or some of them are in alpha. But the good news is, over a period of time, in a quarter or so, we are going to see a lot of CSI native implementation of storage drivers, which will make the life very easy. So what CSI means to Kubernetes users? Basically, it brings in plug-and-play capabilities for a diverse set of storage implementations. This is almost like you don't like a specific implementation, you swap out with another without ever touching your application. Next time when you do a dynamic binding, it basically talks to a brand new storage implementation without your application getting reconfigured or changed. Map existing primitives to storage operations. This is one of the biggest advantages. You can pretty much write a YAML file and use kubectl for performing a lot of storage operations. And this puts the power of storage ops into the cloud native administrator without having to work with a traditional storage admin. And choice of using different storage implementations. I actually mentioned this multiple times as one of the key takeaways from CSI. And advanced storage operations such as application-specific snapshots and bringing in the context of application awareness into Kubernetes applications. So this is just the beginning. As CSI matures, as CSI becomes the de facto, we are going to see a lot of storage operations that are well integrated with native kubectl and Kubernetes workflow. So CSI really fueled the growth of cloud storage. Today, if you have to map out the lay of the land, and if you basically capture and categorize the players, there are public cloud providers, obviously AWS, Azure, GCP, DigitalOcean, IBM. All of them are in the process of shipping a CSI compliant storage plugin for Kubernetes. Traditional storage vendors that are NetApp, Dell EMC, Pure Storage, VMware, all of them are getting onto the bandwagon. They are going to offer CSI compliant plugins and drivers for Kubernetes. And then we have born in the cloud exclusive cloud native vendors like Portworx, StorageOS, Kasten, Robin, and so on. And they are basically building in this abstraction layer on top of cloud ready storage as cloud native storage. And they are almost there, or they are in the process of getting there to offer a CSI compliant plugin. So this is going to bring everyone to a level playing field, and this is the best thing to happen for the community ecosystem and the end users of Kubernetes, because it's going to blur the line between traditional storage ops and cloud native storage ops. So that was a quick walkthrough. I started with the statefulness being an afterthought. Then I talked about the customer journey when it comes to adopting cloud native storage. And then I talked about the challenges and how CSI kind of alleviates the pain and the problems. And now let's take a look at the current landscape. So the good thing about Kubernetes state and the persistence story is the SIG is listening to a lot of customer feedback. And today, if you look at some of the core capabilities, for example, support for local volumes, this has been on the top of the wish list from customers. So local volumes take a host volume or the host path one level above. So in a distributed environment, when you have like multiple nodes and you want to schedule a pod, there is no guarantee that it is going to the same node where you originally used the host volume. Now, thanks to local volumes, you can always make sure that there is a node affinity between the pod and the volume that it is actually using. So you can, when you are creating a PVC, you can add a node affinity, and this is always going to make sure that the PVC, the underlying storage, and the pod are always going to the same node. And this is bringing in the implicit hyperconvergence to Kubernetes. And this is going to help a lot of customers who are prototyping and deploying POC applications without really implementing a complete distributed cloud-native storage. Then we have volume snapshots. This brings in point-in-time snapshots, pretty much like EBS, Azure disks, and GCE persistent disks. So you can actually create a snapshot from an existing PVC, and it is a native Kubernetes resource and object. So you can create a YAML file that says, create a snapshot, here is an existing PVC, and call this snapshot with a specific name. And you can actually maintain a list of those snapshots. Volume cloning, you can clone one PVC and create another exact replica of that, again, using the implicit Kubernetes objects. Volume binding is pretty interesting. This is another development which is still in beta 1.14. And what this does is some kind of a lazy binding, because in Kubernetes, traditionally when you are using dynamic provisioning, you may end up creating a PVC and a PV much before the pod gets scheduled. So what happens if the PVC and PV are created on a specific node and your pod gets scheduled on another node? It will actually be in pending state forever. So thanks to volume binding, which actually brings in the capability of saying, don't create a PV or PVC, actually PVC, not the PV. PV is created much before. So don't create the PVC till the pod is scheduled on a specific node, which will ensure that there is a lazy binding happening only when the pod gets scheduled. And this is going to, again, help a lot of deployments that struggle with making sure that the matchmaking between pod and node is happening the right way. So these are some of the implicit evolutions and advancements happening through the Kubernetes core storage driven by this SIG. And then we have some of the other advancements, particularly from the commercial cloud native vendors. Particularly if you look at how the cloud native ecosystem, the storage ecosystem has evolved. Phase 1 was all about container native storage, basically abstraction. And phase 2 is all about becoming CSI compliant, volume snapshots, replication, hyperconvergence. I think if we have to put all the vendors in a specific bucket, I think most of them are in the phase 2, where we are currently bringing in replication, hyperconvergence, and bringing in the core capabilities to commercial implementations. And as we go ahead in phase 3, we are going to see more of application-aware storage, then business continuity with disaster recovery, complete workload migration. In fact, I got a chance to look at the KubeCon announcements. You will see that many vendors are actually announcing complete workload portability and workload migration at KubeCon. And this is what is expected in the next 6 months. Hybrid and multi-cloud. So Kubernetes is clearly shifting from being a hyperscale environment to more of hybrid. Google Anthos, Azure Arc, VMware Project Pacific and Tanzu, IBM Multi-Cloud Manager with OpenShift, Rancher. Everyone is looking at Kubernetes as a control plane, not just for one cluster, but a meta cluster. And this means a lot of change in dynamics for cloud native storage vendors. So in the next 6 months, we're going to see a lot of changes that are directly impacting the storage landscape through the hybrid and multi-cloud scenarios. By no means is the most comprehensive, but I attempted to put in some of the cloud native storage commercial implementations. This is, again, just a partial list, but it's a sign that this ecosystem is growing pretty fast, and we are going to see more and more players come into this. Apart from the commercial implementations, there are quite a few interesting open source projects that are driving the growth of cloud native storage. The usual suspects like Rook, Ceph, Gluster, and then more recently OpenEBS and Open Software Defined Storage. They are getting a lot of attention from the industry and from the end users. We'll actually see more and more commercial implementations coming out of some of these implementations as well. So I want to quickly summarize by talking about the roadmap. This is something that I've already covered. So what's in store for the cloud native storage ecosystem in the next 6 months? The shift to CSI. I think everyone is working feverishly towards becoming CSI compliant, and that's a great thing. As Kubernetes shifts to being a universal control plane, and thanks to projects like KubeVirt and some of the other things like Virtual Kubelet, where Kubernetes is becoming the control plane to manage non-container orchestration environments, we'll see more and more of shared storage between VMs and pods. And this is going to become a reality, particularly with hybrid cloud, where VMs are going to be first-class citizens. This is going to be an important aspect of cloud native storage. Operators for mainstream databases. We have seen Vitess move from incubation to a graduated project just a couple of days ago from CNCF. Then we have seen how Red Hat is really putting its weight behind pushing the operators. So we'll see more and more operators for mainstream databases. So you'll have a very low-touch, no-friction mechanism to deploy and manage and scale and maintain mainstream databases like Postgres, MySQL, and some of the workloads like Jupyter Hub through operators. And again, it's a great sign. It's a great help for the enterprises. Business continuity for cloud-native workloads. Basically, all the checkboxes that the enterprises clicked for their cloud-ready workloads are now becoming available in cloud native. So disaster recovery, business continuity is going to be super critical for workloads that are running on top of Kubernetes and container orchestrators. Live migration, this is again something that is going to be a very important capability. What VMware has done with vMotion will show up in the Kubernetes world, and we'll actually see more and more live migrations happening across clusters, across regions, across environments. This is something that is going to mature in the coming months. and tight integration between storage ops and cloud native tool chain. We are again going to see a lot of CI/CD integration, blue-green canary deploys, and PaaS-like capabilities, not just impacting the workloads, but even the storage below that. Again, thanks to some of the capabilities like taking snapshots, versioning them, restoring them, you can now create virtualized data and virtualized applications and containerized applications that go hand in glove. And this is going to open up a lot of avenues. So that basically brings my session to the end. Thank you so much for this opportunity. Have a great conference ahead. Thank you.